Magnets. One magnet either repels or attracts another, and nobody knows why. Except you, after watching today's video. Naturally occurring minerals were found to attract iron in the ancient Greek region of Magnesia, and so were aptly named for the area. And these rocks were found to either attract or repel one another. One way to understand magnets is through magnetic domains. You see, unmagnetized iron metal is composed of a whole bunch of tiny little crystal magnets called domains, and they're randomly oriented, pointing in all different directions. But magnetized iron has all the domains aligned. That is, it has a north side and a south side. And that orientation is what allows it to become a magnet. During the magnetization process, the domains flip suddenly. This flipping can be made audible. I have here a small piece of nickel, which I'm placing inside of this coil of wire. Any rapid changes in magnetic field will sound on this speaker here. I also have a very strong magnet, which I placed on the north end of this little magnet. When I bring it close to the nickel, listen. Do you hear the domains flipping? And there you have it, a new magnet. This iron paperclip can be magnetized by this magnet. The magnetic domains in the paperclip can be destroyed by heating. And the magnetism is lost.
Besides iron, cobalt and nickel are also magnetic. Their proximity on the periodic table lets you know that magnetism is a result of electron valence. That is, all magnetism is caused by electrons.
This coil of wire with a looping current is acting just like a bar magnet, causing compasses to point out of north and into south. Out of north and into south. Could it be that the electrons orbiting the iron atoms are the net cause of magnetism? That is, could it be that circling electrons are causing the magnetic field? In 1915, Albert Einstein and von der Haas ran an experiment to check that it was the orbiting electrons that caused magnetism. The results were negative. Later on, it was discovered that electrons had a property called spin. That is, the electron was spinning as it circled the nucleus. It's the alignment of these electrons' spins that results in the magnetic properties of iron. And this only occurs naturally for iron, nickel, and cobalt because these atoms have an unusual double valence, in which their two valence electrons are paired with parallel spins. A very rare circumstance indeed.
In summary, a magnet is a collection of microscopic crystal domains that have their electron spins aligned. This is particularly prevalent in iron, nickel, and cobalt, in which there is a pair of valence electrons with their spins aligned. A quantum mechanical effect evident in our everyday lives.